other one by
Yeah, yeah.
either plugging in a headphone, or you just make the voice zero, that is sound zero.
Okay, I have muted the other one. Now it's
Okay.
okay.
Yeah, now it's fine.
Now it's coming okay, fine. Yeah.
Yeah. Okay, so I'd like to begin by thanking the organizers for inviting me for this colloquium. So the topic today is about periodically driven readback chains, and it will mostly be based on a series of works that I did with my student Bhaskar Mukherjee, who just graduated from IACS. Saurabh Nandi, who was a student with Arnav Sen, and he is now at IIT Bombay. Arnav Sen, who is my colleague at IACS, and Professor Diptiman Sen from IISc, whom I'm sure all of you know. So, if you are interested in more details of this work, and I'm just going to give you a sketch of what has been done, these are the papers which you may look into. Okay, so these are the things which has all the details of the work. So here is a brief outline of the talk. First, I'm going to introduce the subject a bit and talk about why these experiments on Rydberg atom has attracted so much recent attention, and in the process introduce something called quantum scars. Then I'm going to talk about a model and drive the model and talk about a Fluke Hamiltonian corresponding to that model, and study the effect of scar in the Fluke physics of this model. Okay, so these things are going to be clear as I go on, and there would be a series of unusual phenomenon that I'm going to chart out, which happens when you periodically drive this kind of models, and that's the main point of the talk. So let me begin by introduction. The first concept that I would like to introduce is called the eigenstate thermalization hypothesis. So to understand what this is, so first let's ask the question, so how can we chart out the evolution of a quantum state for a non-integrable many-body system? So for example, I could ask the question, what would the expectation value of a typical local operator behave at long times in the presence for this kind of many-body states? So if I take any local operator and take its expectation value as a function of time, how would it behave? Now, of course, if the state is an pure eigenstate, then nothing evolves. But I'm obviously not talking about that kind of state. But I am talking about a generic state created out of superposition of many such eigenstates. And that's what makes the question non-trivial. And the answer to this question, it turns out, requires understanding of the properties of the matrix element of such operators between any two eigenstates of the system. Okay, so imagine that I express my wave function in the basis of this eigenstate, then the matrix element, or so the time-dependent matrix element of the operator will require the knowledge of matrix element of this operator between any two eigenstates. And what eigenstate thermalization hypothesis tells you is that it provides a conjecture, this is not yet proven, regarding the nature of such matrix element. All it says is that for a typical local operator, the answer to this question about this matrix element between any two eigenstate is that it's diagonal. So that's the first term, and the off-diagonal part is suppressed because it has an exponential to the power of entropy, S of E, which is an extensive quantity. So if you take the system to, if the system is large, this quantity is exponentially suppressed. And what are these diagonal terms? These diagonal terms apparently is the value of this operator that you would get if you calculated it using a canonical ensemble or a microcanonical ensemble with an average E bar, which is basically the energy of this state. Okay, because it's En plus En by 2, but if you have delta Mn, it's just En. Okay. So this is a surprising conjecture, but it has been proven to be right for many cases, and to the extent that this has now become the standard in the field. That typically, if you ask that what's the long time value, well, the answer is whatever ETH tells you. Okay, so what it tells you is that for a large enough system, the answer to this question of how would the expectation of a typical local operator behave at long time is nearly identical to that obtained using a microcanonical ensemble at the average energy. Okay. So, so let's take that, and then you see, for there are many ways in which this ETH can be violated. Since this is the norm, what is interesting is how this norm can be violated. So the first thing is that this doesn't work for integrable models, because this ETH, although I haven't really given its details, requires ergodicity of your system. And if you have an integrable model, you don't have ergodic behavior because you have constraints, or and this constraint condition essentially prevents the system from exploring the whole phase space, and therefore ETH doesn't work. To see this, there is this very interesting expectation. So you construct a state E, okay, which has a fixed energy. So you are now considering it to be in an eigenstate, but this you can do, and consider a local operator which is density at nearby sites, okay, and you consider the expectation value of this between these eigenstates, energy eigenstates, okay. So you see that if the system is non-integrable, where you have added an interaction. So here what you are doing is, this plot is for a fermionic chain in one dimension, and in one case you add an interaction, and those are the red dots. Okay, so you see that for most of the energies it's within a line, and this spread of the line depends on the system size. Because you have a finite system size, ETH is not exactly valid. It becomes exactly valid at infinite system size, and one can show that as you increase the system size, the width of this line decreases. So essentially everything falls roughly around the average energy out here. However, if you now turn off the interaction and make it a free chain, which is an integrable model, those are the blue dots, and you see that it's nowhere close to the ETH predicted value. So this is one way in which ETH can be violated. The other way in which ETH is known to be violated is when the system becomes non-ergodic due to localization of all states in Hilbert space due to very strong disorder. Okay, if that happens, this ergodicity condition is again violated, and it is known that ETH is not applicable. What I'm going to talk about today is violation of ETH due to a special class of eigenstates in the Hilbert space of the system, which leads to long-time coherent oscillations. Now, what does this mean? So you see that if the long-time time average expectation if ETH holds is given by a constant term, okay? So if you look at, which is just this time average of the expectation value of operators. So what it tells you is that for any operator, if you want to look at the long-time value, all the quantum oscillations are going to die out, and you are going to get a constant steady state where the value of the operator is identical to its average microcanonical value. Okay. However, this precludes the presence of any long-time coherent oscillation. And when I say long time, I mean time scales which are much larger than any typical time scale of the system. Typically, what happens for non-integrable system is that the quantum oscillations die out very fast, and what I'm going to see in the class of system that I'm going to study.
Slide, because ultimately when you carry it over to the Floquet case, your omega is known to be very large.
And first of all, I haven't even so long time is very well defined in that case.
Yeah.
So it's really the minimum of, so it's the maximum of time scale given by either the system energy scales or the drive. That's what is used to define this long time.
Okay. And the blue dots that you have is operating system.
That's right. So I'm just plotting the density correlation of those.
Oh, okay. All right.
Okay.
And the interaction is also of density correlation type.
The interaction was, yes, of the density correlation type.
Yeah.
Sure.
Okay.
Okay. Any other questions? Okay, if not, let me just go over to the next this thing. So let me now try to define what these cars are. Now these cars, essentially, they are known in classical context for a very long time. So apparently, these are best understood from looking at the trajectory of a classical particle in a billiard table known as the Bunimovich stadium. What happens is the following. So if you have a stadium which is something like a rectangle and a cylinder fused together, you take a billiard ball, consider the stadium to be frictionless, and then you hit it. Okay. So for an arbitrary trajectory, this thing is going to keep on moving out here. And at the end of the day, it's going to fill up all the space in the stadium uniformly. That's what, in this context, that's what ergodicity means. And the trajectory spreads over the entire phase space. However, there are special initial points for which the long-time distribution in phase space is non-uniform. For example, a simple example of this, there are many pictures like this, but the simple example of this is that if you start from this point where my cursor is and hit it straight, okay, so that it just covers one trajectory on and on and on. It doesn't spread, okay. So that's a trivial example, but there are non-trivial examples like this. And in one such non-trivial examples, if you look at the trajectory, after a very long time, you will see that some parts are covered a larger number of times than the others. Okay. And these essentially forms the scar-like patterns because of these darker spots, and they are known as classical scars. Now, what is the quantum mechanical version of this? The quantum mechanical version of this is understood by taking a Schrodinger equation where the potential mimics this this stadium potential. Okay, so there are some hard walls of this shape, and one seeks the probability distribution of a Gaussian wave packet centered near or on a classical orbit, something like this, at t equal to 0 at long times. And one chooses a classical orbit which is known to generate scars in the classical problem. Then one can show that the dynamics obtained, if you calculate the probability of finding the particles at a given time t in the long time limit, you get patterns like this, which is example of classical scars. Okay, so quantum scars. So what it means is that there exists non-uniform distribution of probability density at long time due to existence of a special set of eigenfunctions which you can show are responsible for these non-uniform trajectories. And basically these eigenfunctions are the ones whose probability amplitude peaks around these classical periodic orbits, or the classical orbits which is scar-like. So those are single particle quantum scars that one knows of. Okay. Is there a question?
So Krishnendu, just one quick question. The quantum scar that you are showing, it is just the probability density that we are measuring.
That's right.
So this black dot and white dot, it represents the intensity, right?
It represents the intensity. Black means larger intensity.
Okay, fine.
Okay. So in the context of many-body physics, the definition of these scar states are somewhat different. So as you know, in a quantum Hamiltonian, many-body Hamiltonian, if you look at the Hilbert space, the low-lying states have zero energy density. That is, it has an energy which, if you define by the volume, in the large volume limit goes to 0. However, in the middle of the spectrum, the energy states have a finite energy density, which means that E over V, or in this case E over L for one-dimensional system, essentially is a constant. Okay, so these are typically called finite energy density eigenstates, and this is there for any quantum Hamiltonian, that many-body Hamiltonian that you can think of. Now, typically, if you take one such eigenstate and you construct a density matrix out of this by taking outer product of the eigenstates, and then construct the half chain density matrix, which means that after having constructed the density matrix and calculating its matrix elements in position space, you throw out those elements which are there in one half of the chain, construct the resultant density matrix, and now because you have thrown out half of the chain, your density matrix will give you an entanglement. Okay. So typically, if your energy density is finite, your entanglement will follow a volume law. This is well known because a finite energy density eigenstate is an example of something called a thermal eigenstate, and for any thermal state, entanglement entropy is follows the volume law. It's extensive. Density, they are in the middle of the spectrum or close to the middle of the spectrum, but they have much lower than volume law entanglement, roughly area law entanglement. So they have to have these two features. And in many systems where particularly there are constraint condition in the Hilbert space, they show up. The general condition required for their occurrence is not known. However, it has seen that whenever your Hilbert space is has some constraint conditions, which we'll see in the case of Rydberg, these curves show up. So because they have this area law entanglement and they are athermal, they violate TTH. This is well known, and they are in one dimension. They are half chain. Measure this half chain entanglement entropy for all your eigenstates and plot them as a function of energy of this eigenstate. You see that most of this black band are the ones with large S, which is this volume law states, okay, thermal states, and then there are this set of bands towards the bottom, which is there at the middle of the energy, which means it's in the middle of the Hilbert space. However, their entanglement is very low, so they have area law, and these are the scars. Okay, so that is the point. So these are what we call quantum scars. Now these states essentially are athermal; they are not ETH obeying, so they can in principle lead to long time coherent dynamics, and in this case it turns out that they do. So one of the things that is important is that if you start from an initial state and you sort of evolve the state according to some drive, as long as these scars have finite overlap with this initial state, they control the dynamics. Okay, and then you can see these long time oscillations. So this means that in a many body system, starting from an initial state, you can, in the presence of these scars, have these long time oscillations rather than typical thermalization, which was a surprise. Okay, when they found out in the Rydberg chain, and I'm going to come to details of that. So here is
Krishnendu, is there a sort of a priori reason that the volume law wala jo states they do not fluctuate as much, and the area ones they do?
No. So see, the thing is that okay. So the thing is that these volume law states, they are all ETH obeying. Okay. So if you calculate the dynamics of any state within those, what will happen is you are just going to get the ETH prediction.
So when you say dynamics, you simply, according to the equation of motion, you just evolve them.
That's right. Evolve them and see what happens in the long time.
What happens. Yes.
Okay. So the blue lines here is what happens when you have scars, and the red line is what happens when you don't have scars. Okay. So you see the difference. These oscillations die out within the first 20-25 cycles if you don't have scars, and then you have just a flat line which is this ETH predicted value of the operator. However, if you have scars, you see that it keeps on oscillating for very long times. And here everything is in typical units of system timescale, which is 1. Okay. So now let me come to this concept of Rydberg chain. So these Rydberg chains, which are the experimental. Yeah.
What did you say? That the energy is in, so the time is in inverse of energy, right?
That's
this
right.
Time is okay. Yeah. Okay.
All right. So system timescale is of the order 1.
Okay.
Yeah. So now let me come to the experimental platform for this this kind of Rydberg chain. So what happens is that you have a bunch of atoms, which are these 87 rubidium atoms, which is made cold and put in a one-dimensional optical lattice. Now it turns out that these atoms have two states which are important for us. One of them is the state G, which is this 5s half state, which has a total spin of 2, and typically these atoms are in all spin down states, which is mf equal to -2. And then there is an excited Rydberg state, which has J equal to half and Mj equal to -half. And this is a really excited state. It is 71 s half, okay, for the Rydberg this thing. So it turns out an atom to this R state. If there is an atom in a near, so you excite state. If the interaction between problem, and in experiments, this is a tunable parameter. You can tune this by adjusting the energy levels out. This is called the detuning frequency out here. Okay. So I'm not going to explain in details what this is. So for an effective low energy Hamiltonian of this Rydberg chain, what do we have? We can say that we have a probability of exciting atoms from G to R. So we have a fixed we have a number of these Rydberg atoms, and there is a energy cost of putting these Rydberg atoms, which is of course supplied by the external potential, external lasers, and we call that delta I. Then once you excite an atom in the upper state, it can spontaneously flip back to the lower state, or an atom can be spontaneously excited to the upper state. So you have a term like this, which tells you that there is a probability of excitation of these atoms from the ground to the excited state. Okay, and this is there because you have a laser turned on, so you can always excite an atom spontaneously from one state to another, or the atom can just throw out its energy and come back to the ground state. So that's your omega times sigma. And then if you have two Rydberg atoms at sites I and J, there is a dipole potential in between them. Okay. So the ground state of so what is the ground state of this Hamiltonian? So for example, if your delta is much larger than omega and omega, then of course you want to form as many Rydberg excitations as possible. Okay, so that's preferentially making Rydberg excitation. However, if your Vij is very large, that's going to obstruct this Rydberg atom formation, this excitation formation. So if you tune your Vij so that it becomes really large for neighboring sites, but not so large for others, and experimentally they can do this, then you create a state which is Z2 ordered, which means that at every alternate site, you form a Rydberg excitation. Okay. Similarly, by tuning this Vij, you can form a Z3 ordered state or a Z4 ordered state, and so on. Okay. And sorry. And
Krishnendu, I didn't get your last term in the last slide. Can you just go to
this one?
So
Vij
your n equal to 1 plus sigma z by 2. I mean 1 plus sigma z whole divided by 2. So that makes it that makes your densities fractional, right?
No, it doesn't. Sigma z takes value 1 or -1.
That's right. So it's 1 minus 1, and you have a unit matrix, identity matrix.
No.
So yeah, it's going to add up.
1 or 0. N is 1 or 0. Okay.
Yeah.
Okay.
Yeah.
So the thing is, so now you can have Z2, Z3 or Z4 ordered, and then what happens is that as you increase this detuning, you can go into these states, and if the detuning is really small, everything stays in the ground state, so there is no Rydberg excitation. Okay, so that's basically the phase diagram. So what people now did in the experiment is that they started from this Z2 ordered state. Okay, so where you were in this Z2 ordered state, and then they quenched from this Z2 ordered state to the disordered state, and then they wanted to see how the system evolves. So this is a sudden quench. So you change this detuning very fast. Okay, and what do you expect? You expect that you expect ETH, because this Rydberg chains is a non-interacting, non-integrable system. It's an interacting many-body system. So you expect that there would be some initial oscillation, and then you will level up.
Krishnendu, sorry to interrupt once more. I didn't get the list of symmetries of the Hamiltonian.
I didn't probably say anything about that. So what do you mean the list of symmetries?
I mean, what are the symmetries of this Hamiltonian?
Can I actually come back to that a little later when I write this in terms of the spin language? That would become easier. Okay.
Sure.
Okay. So the thing is that what they found is that instead of this ETH-like behavior, they have really long time coherent oscillations. And then they were trying to, so this is Avanin's group, and then they explained it, this behavior in terms of quantum scars. Okay. That this Z2, essentially this state has a high overlap with these Carl-like states. And therefore the dynamics starting from the Z2 state, the sudden, dynamics after the sudden quench, they always proceed by by these Carl states, and therefore they lead to long time evolution. So that's that was the excitation. That was the excitement in the field regarding these Carl-like states. So what we wanted to do is to take these Rydberg chains and periodically drive that and try to see. And now you see that the dynamics would be controlled not by the Hamiltonian of the system, but by the Fluke Hamiltonian. And what we wanted to see is that what the Fluke Hamiltonian gives you. Okay. So
is this more like the like a checkerboard, and then a dimer checkerboard kind of, this Z2, Z3, Z4, etc.?
Yeah, these are, except that these are in one dimension. Okay, you don't have a 2D pattern, it's just in one dimension.
1D, okay, yeah.
So now I'm going to explain a model which essentially tells you what the relation of this experimental system is with the model that we study. So this model is an effective dipole Hamiltonian, where D is a dipole creation operator, dipole destruction operator, and DL dagger is a dipole creation operator. This is a thing that we studied long back, much before any of this came, just out of curiosity. So what this does is it describes a set of dipoles in 1D lattice whose numbers are not conserved. So you can spontaneously create and destroy dipoles. Now the presence, so this dipole model by itself would be solvable. Of course, it's a very simple model, but it becomes non-integrable because of the presence of constant. The first one is that there could be at most one dipole on a given site or link. And the second one, which is the more important one, is that there couldn't be any dipoles on nearest neighbors. Okay, 2 dipoles on nearest neighbors is forbidden. So NL plus 1 is always 0. So the presence of this constraint of not having 2 dipoles on adjacent link makes the model non-integrable. How do you see that? You can map this dipole model to a spin model by mapping the number of dipoles to sigma z and dipole creation and destruction to sigma x and y, or sigma plus and minus. And then the projection of having, so then one can define a projection operator which goes to 0 if the dipole state is occupied. And then this dipole Hamiltonian can be exactly written in the spin language by using this projection operator. So you have a sigma x, which is like D plus D dagger, and the constraint is implemented by putting in 2 projections operator at 2 neighboring sites, so that the sigma x can only flip dipole if it doesn't have a dipole on neighboring sites. Okay, and then of course this nz is sigma z, and we have ignored a constant. So this now becomes a term which is like sigma x tilde, which is this whole operator, projection sigma x projection, times lambda times sigma z. Now notice that this, okay, so now one can look at the symmetries of this Hamiltonian. Okay, so these are the same as the Ising symmetries. I hope that answers the question. If not, I can discuss more. Saurabh, was that you who asked the question, or?
Yeah, I did. Okay.
So is this okay, or? Okay.
Yeah, it's okay. It's okay. When you write it in terms of the spin Hamiltonian, it becomes more clear.
Yeah.
Because so I thought I would need it to understand that phase diagram. So that's how at that time I asked.
Yeah. Okay. So now you see in the dipole model, if I tune my Rydberg, so this dipole interaction such that VI plus 1, that is the dipole interaction between neighboring sites, is large compared to all other scales in the problem, but VI plus 2 and or VI plus 3 is small, then this Rydberg Hamiltonian can be written in terms of a constant model like this. And then this is exactly mapped onto this spin model. Okay, so it's really identical. So what we are going to do is to study this spin model, and whenever necessary, we are going to draw a parallel with the Rydberg model. Okay, this is what Abanin's paper also did. The difference is that we are now going to study the Fluke physics of this model. Before doing that, let me quickly tell you about the phase diagram. So in the dipole model, if you have a large, so let me just go here. So if you have, where did you go? If you have a large positive lambda, which is the cost of creating dipole, then you are in the dipole vacuum phase. That is, the ground state doesn't have any dipoles. However, if you are large and negative, then you form maximum number of dipoles, but that is just half the sites because you have this constraint. And therefore, you can form dipoles either at the odd number of sites or the even number of sites. And the ground state spontaneously break this Z2 symmetry, which is same as the ferromagnetic phase of the transverse field Ising model. And then in between, it turns out that there is a quantum phase transition at some fixed value of lambda. And this belongs to the Ising universality class. Okay, so that's roughly the equilibrium phase diagram of the model. Now I'm going to study the Fluke Hamiltonian of this model under a periodic drive. And what we will do is that we are going to study a simple square pulse protocol where we are going to drive the sigma z coefficient, that is this lambda of t, as a function of time. And this would be by the square pulse protocol where lambda of t would be plus lambda or minus lambda for the first and the second half of the drive pulse. Okay, so that the evolution operator is just given in terms of h of lambda and h of minus lambda. Okay. So, and then what we are going to do, we are going to calculate the expectation value of operator, typically a density correlation operator of this dipole. Okay, in the presence of this drive. So out here, where I'm going to make one comment. So we do this by two ways. The first is that we do this exactly for a finite chain, exactly numerically using exact diagonalization, and that's all the numerical result that one wants to see. And then we are going to construct an analytical but perturbative Fluke Hamiltonian and compare our results with those. Okay. Now, what do you do when you have such a protocol? Okay, the first thing you do, sorry.
Krishnendu, this was my initial question. Then when you are calculating the expectation values, this is an out of equilibrium system. So right. Whether your Fluke things are, so there has to be a very large omega in order to perturb your system.
No, not really. That depends on, no, not really, because Fluke systems can be, periodic drives are described by Fluke system irrespective of the largeness or smallness of your frequency. However, if you are approximating the Fluke Hamiltonian by something like a Magnus, then you are certainly going to be in the high frequency regime. But we are not going to do just Magnus. Okay. We are going to go beyond Magnus, and the numerics is exact at any frequency. Okay. One can still calculate a Fluke Hamiltonian. That's for any frequency, but Magnus is of course for only high frequency.
Okay.
So first, let's talk about Magnus since this came up. So if you have a high frequency, if you are at the high frequency, then you can do a Magnus expansion, which is a 1 over frequency expansion in some sense. I'm not going to get into the details of this, but the point is,
Krishnendu, there's a hand raised by Ranjini.
Yeah, Ranjini, please.
Hi. So you said you're not using the Magnus expansion to write the Fluke Hamiltonian, right? So you're just using the time ordered product and then taking a log. Is that what you mean?
No. So this is done numerically. Okay. So what we do is basically numerically, we diagonalize h of lambda and h of minus lambda exactly. Okay.
Okay.
And then use those eigenstates and eigenvalues to construct U. And then we just take, we just calculate this frequency. This is numerics, okay?
Okay.
Here
Okay.
we don't calculate the Fluke Hamiltonian, we just calculate the expectation value of the operator. Now for the Fluke
Okay.
Hamiltonian, what we do are two things. The first one is this Magnus expansion, and the second one is something called the Fluke perturbation theory, which I'm going to discuss. So just hold on for a second.
Okay. Okay. Thanks.
Sure. So, okay. So what happens now is that for the Magnus expansion, what we do is that we basically do the standard thing. So the first order term of Magnus is just the average Hamiltonian. The second order is complicated correlators, etc. But all of these can be sort of calculated order by order. But let me try to give you the gist of it. The gist of it is that there is a class of terms which is which gives you just sigma x tilde and sigma y tilde, okay, which with a rotation is just like what you had for the original Hamiltonian. Remember, in the original Hamiltonian, what I had was a sigma x tilde and then a sigma z, okay. So this sigma x tilde term is, so in the Fluke Hamiltonian in the high frequency regime, remember this parameter gamma is lambda by omega, or lambda times capital T, and delta is W times capital T. So if I am in the really high frequency regime, all I have is sigma x tilde. And that is understandable because there the Magnus is just the average Hamiltonian. And because I am driving it by plus or minus lambda T going to plus or minus lambda in the average Hamiltonian, this sigma z term just cancels. And all you have is sigma x tilde. Okay. So, and we also focus on the regime where this lambda is large compared to W. So we are in the large drive amplitude regime, so to speak. So there is a class of terms which gives you just sigma x tilde and sigma y tilde. Okay, so this is what is called as the renormalized PXP, because this can be mapped onto the PXP term, which is like sigma x tilde up to a rotation. So if you just rotate in the sigma x sigma y plane, you are going to get this term. Okay. Then there is a class of term which cannot be mapped into this PXP kind of terms. Okay. So those are the higher order terms, and this represents deviation from the typical PXP Hamiltonian form. Okay. So that's the result of the Fluke Magnus thing. Okay. So one can do this frequency expansion in higher orders. We did this, but that's not the main point. So, but this Fluke expansion only captures the physics at high frequency. But what happens at intermediate frequency? And to address that, what we do is that we take a different type of perturbation theory, which doesn't take the frequency as the small parameter, but one over frequency as the small parameter, but it takes the inverse of the drive amplitude, that is W over lambda, as the small parameter. So here there is a technique for this. This is developed by Diptiman Shen and also even also by this guy Nigel Cooper and Thomas Bitlowski. And so what you do is that first you tackle the term which is large, and for that the evolution operator is just a sigma z term, which you can write exactly, and then you do first order perturbation theory to find out the correction to this U order by order. Okay, and H1 is the term which is proportional to W, which is the small term. And once you do that, your first order term gives you a PXP kind of result, which tells you that the coefficient of this PXP is just sine gamma by gamma, where gamma is lambda times T, T being the drive period, divided by 4. And this point is going to be important in subsequent discussion. So please remember that this coefficient, what we found, is sine gamma. Okay, so there is a sine gamma term. So it vanishes at particular frequency. That's important. And then you can go to second and third order terms. The second order terms seem to vanish because of some symmetry, which I'm not going to get into details of. And the third order term gives you some non-PXP type of results. Okay, so this
But Krishnendu, that is not sine gamma. It's like sine gamma by gamma.
That's
right.
right.
So that
So
has
gamma equal to 0 is going to remain finite, but for all gamma equal to n pi, where n is not equal to 0, it's going to vanish. Yes.
It's like the J0 term.
That's right. Because you see, this gamma equal to 0 is the real high frequency term. Okay, and there you see that you recover the PXP result. Cos gamma goes to 1, sine gamma by gamma goes to 1, and sine gamma goes to 0. So it's just the PXP.
What is the original reference for this? Diptiman's paper.
Original reference is Diptiman's paper and Thomas's paper, and both of them are there in the paper that I showed you in our work actually.
Okay.
So, yeah, those references are there.
Yeah.
So, and then you do the third order thing, which is also, gives you this non-PXP term. And now, armed with this, let's see what this dynamics of correlation gives and what we can do to explain that. Okay. So, can you tell me how much time I have?
So you have 20 minutes.
Oh, okay, good. So I'll finish in time, I guess. Good. So now let's come to the dynamics of this correlation function. So what we do, we start from an initial Z2 state, which is this up-down spins, which means one Rydberg excitation every alternate side, and then compare the time-dependent correlation. Density correlation function. So we take one of the Rydberg atoms at site 2 and another at site L+2, which is 4 for us, and study this correlation function as a function of stroboscopic time, that is the number of cycles. Okay. Since we are doing Fluke physics, we can only study stroboscopic times, that time in integer multiples of the drive period. Okay. So here is the behavior at different drive frequencies. So when my omega d is very large, my Fluke Hamiltonian is approximately same as the original PXP Hamiltonian, and I see these long time oscillations, provided I start from the Z2 state. Here, notice that this red line essentially gives you the same dynamics of the same operator, provided I start from a different state. In this case, the Rydberg vacuum state. Okay. Here, for the Rydberg vacuum state, I see this ETH-like behavior. Okay, it goes to a steady state and remains there, but there is this long time oscillation for the Z2 state. This is what. So this is same as what Abanin and others saw. The high frequency limit is roughly like the quench limit. Okay. However, if I go to very low frequency, where the Fluke Hamiltonian is not just the PXP term, it's much more complicated because there are other terms in the problem. We don't really know at this low frequency what the analytical form of the Fluke Hamiltonian is, but we can only guess that it's going to be a very complicated thing because at low frequency, the Fluke Hamiltonian is completely a complicated beast. So there you see that these long time oscillations are gone, and the dynamics obey ETH. It just goes to the steady state value. And we have checked numerically that the steady state value is exactly the thermal value which this ETH predicts, with the average energy and everything. Okay.
This W going to 0, wouldn't it? W by lambda. W by lambda going to 0, won't it get you to the small frequency limit, or no? No, I missed something.
W is the coefficient of the sigma x tilde term. Okay.
That's the interaction.
So W here is the coefficient of the sigma x tilde term, and lambda is the coefficient of the sigma z term. So these are the amplitudes of the two terms, and this being a small parameter means your drive amplitude and not frequency is large.
Oh yeah. Okay. Yeah. That's
okay.
Yeah.
So then in the intermediate regime, something funny happens. So if I am at omega d equal to 1.3, which is an intermediate frequency, I see this ETH-like behavior. However, at lower, and mind you, lower and not higher frequency, we find an oscillating behavior with long-term oscillation. This means that there must be reentrant transitions between this long-time oscillation and ETH-like behavior. Okay. Now, concomitantly, we look at the half-chain entanglement entropy of the eigenstates of the Fluke Hamiltonian. So at high frequency, we find that there are this, of course, this black semicircular band, which is the thermal band. And then there are a lot of states out here, which are the scars. Okay, these are lower in entanglement, and the red ones are the ones which control the dynamics because they have a large overlap with the Z2 state, the initial state. For omega d equal to 100, where the Fluke Hamiltonian is almost same as the PXP model, we find that there are these scar states and there is a thermal band. By omega d equal to really small, everything is within the thermal band. Okay, so there are no scars. The red dots, which shows states with large overlap with the Z2 state, has now gone to the thermal band. So in these frequencies, the Fluke Hamiltonian doesn't have any scars. In between, you see that for omega d equal to 1.3, I don't have any scars. Everything is in the thermal band again. Here, there are scars, but they are not as low as the one for omega d equal to 100, but nevertheless, they are out of the thermal band. So you see again that the presence and absence of scars are tied to these long-term oscillations. These are all numericals, and we are going to try to understand this from this. So the first thing we try to analyze is the high frequency regime, which is this omega d equal to 100. Okay, so as I come down in frequency till omega d equal to, let's say, 20 or so, the Magnus expansion, and we did it to 11th order. So the 11th order Magnus expansion essentially gives you a very nice agreement with the data. And the decrease in this, so here we plot this oscillation frequency as a function of this drive frequency. And the decrease in the oscillation frequency occurs because of these terms. Because the oscillation frequency is controlled by the coefficient of the sigma x and the sigma y term, and as I increase this, decrease this frequency, gamma increases, and therefore the oscillation frequency, gamma and delta both decreases, and it turns out that the oscillation frequency decreases. Okay, those are just energy separation between consecutive scars, and that's what controls the oscillation frequency of this in this regime. It turns out that the scars are amazingly regular in frequency, and therefore you have only one oscillation frequency in this regime. Okay, so in the intermediate regime, something interesting happens. So if I look at this drive frequency, which is 8.25 in units of W, okay, I find this oscillation. As I go to omega equal to 8, lower the frequency a little bit, this oscillation goes away. So you see that there are some initial oscillation and then you reach the steady state. At around omega equal to 7.75, which by the way corresponds to lambda t by 4 equal to pi. Remember that here I had a sine gamma over gamma, okay, where this gamma is lambda t by 4. So this 7.75 in our units corresponds to gamma equal to pi. Oops, sorry, let me just go back to that slide. So this corresponds to gamma equal to pi, and here you see that the oscillations are almost completely gone. And then when you move past this point, the oscillations come back. And similarly with scars. So with 8.25, you have some scar states. At 8, there are just a few. Everything almost moves in the band, thermal band. At 7.75, they move well inside the thermal band, so that everything is dominated by ETH. And then at 7.5, you come out of this, and there are a few scar states also.
So,
oscillations. Yeah.
So Krishnendu, I have just one quick doubt that so when you define the scar, it may have a periodic oscillation, or it may have quasi-periodic, and other harmonics may also be present.
In principle, yes. Here we, of course, you see the scars are eigenstates. They don't have any oscillations correspond to them. Their separation of their eigen energies is what gives rise to these oscillation frequencies. Okay. So here it turns out for most of the cases, the scars are amazingly regular. So you just see one oscillation frequency. But if you have a situation where there are multiple scars, scars with multiple energy separation, then of course you are going to see a much more complicated dynamics. But that doesn't happen here.
Because for 8.25, I can see quasi-periodic. It has the 2 frequency.
Yeah, so you are going to see that, if you look at all the energy separations of the scars, what you would see maybe that there is a very small difference between the scar energies, and that's what gives rise to this pattern.
Okay.
And this attachment of the scars and detachment of the scars, they only happen once, or they
no, I'm going to show you that's the main point actually. So why does this happen? So what happens is that this can be understood from the Fluke Hamiltonian. So you see that 7.75 turns out to be the point where this gamma is pi. If gamma is pi, you see that this first order term in the Fluke Hamiltonian, which is usually large compared to the higher orders, because gamma is a large parameter, that goes to 0, okay, because of this sine gamma. And then the dynamics is entirely controlled by this third order term, which is much more complicated, and they are not of the PXP form, and they don't have scars, okay. So at this frequency, what happens is that the first order term essentially vanishes, and the third order term gives you a dynamics which is all thermal. Now, it turns out that this vanishing is the main point which allows you to go from a long-term oscillation to a thermal behavior. And this not only happens at gamma equal to pi, it happens at gamma equal to n pi for integer n. And as we tune this frequency between 20 and 2 in some units, this lambda over omega d, we find that there are multiple such regimes. So here, this is the phase diagram. The thermal behavior occurs around these yellow lines, okay, roughly around spread, which is given by these dark shades. And as you go in lower frequency, these thermal behaviors become more and more frequent, and they ultimately cover the entire phase diagram at very low frequency where there is no coherent oscillations. And at high frequency, these white regions are the coherent oscillating behavior.
So there are, fifth order and seventh order and ninth order dates, etc. They start contributing to the lower ones, right?
They will start contributing, but the point is that scars are only there if you have a sizable first order term which is large compared to all higher orders.
Okay.
That doesn't happen when your gamma becomes n pi, and those are the regions where you have thermal behavior. Okay, and you see that sine gamma by this is also a curve of sine gamma by gamma in some units.
Yeah.
Okay, so that's why you essentially find that they become so because the n becomes larger and larger, these regions become more and more frequent.
In fact, it's controlled by that.
It's controlled.
It's mainly controlled. That's what you said at the beginning also.
That's right. So the point is that what do we find here, that you can tune the coherence property of a driven many-body system by tuning the drive property. You can actually move from an ergodic to a non-ergodic behavior just by tuning the drive frequency. And that's the main message that I wanted to give in this talk. Okay. So this is also one way to control ETH-like properties in a given driven system. A transition between a coherent and a non-coherent behavior, ergodic and non-ergodic behavior.
So it just goes back to your billiard table, the rectangular and spherical, that as you decrease your frequencies, then it starts, getting concentrated at parts of the billiard table.
Actually, yeah. So the point is that no, it's the other way around. As you decrease frequency, it becomes more ergodic.
Yeah, the other way.
But,
yes.
Yeah, the other way around. But with increasing frequency, you can find out special regions. These would be the characteristic analog of the trajectories. These frequencies would be the analogs of this classical trajectory. So if you choose your dynamics to start at these frequencies, that would be analogous to choosing a classical trajectory in that billiard problem, which is going to give you, the scar-like behavior. Okay. Ergodic-like behavior, that is. Yeah.
Yeah.
Yeah. Okay. So now I'm going to talk about, for the next 10 minutes that I have. Do I have about 10 minutes, or?
Yeah. Krishnendu, you can go ahead. Yeah.
Yeah. So just 10 more minutes. Okay. I'm not going to torture you more, but let me just use this thing. So the thing is that what I'm going to do now is that talk about correlation dynamics, which starts from the vacuum state. That is the Rydberg vacuum. So my initial state is the one where the ground state of the system doesn't have any Rydberg excitation. So I again do the same thing that I did with this Z2 thing, and here is the plot of the. So let me just come to this. So what did I do with this Z2 initial state? I plotted the density correlation function. Okay, and this has a long time value, let's say. So it turns out that if you have this coherent oscillation, the long time average value is above the thermal band. Okay, so what is predicted by ETH? That's another signature that ETH is violated out here. Here, what I do is the same thing, but I start from the zero state, okay, the Rydberg vacuum. So here what happens is that if I'm at really high frequency, I know that the Rydberg thing, so if I go back, so if I, so this is my diagram, the red one is my diagram for this vacuum state, okay. So you see that at really high frequency, I find that I have a ETH obeying dynamics. So everything is thermal. So here, what I plot is the long time value of this correlator, and this dotted line is the ETH predicted line. So at high frequency, I find out that I obey ETH. Then as I decrease my frequency, I see oscillations here where the long time value is super thermal. Okay, which I'm going to show these plots, but here the long time average value is larger than the ETH predicted value, which is a signature of oscillations, and we are going to see that there are oscillations. But two more interesting thing happens. So at some special values just below omega d equal to 8 in units of W, I find that there is no dynamics at all. So this is an example of dynamic freezing, where the system completely freezes, it simply doesn't evolve. Okay, so that's one new thing which is not there in the Z2 scar. And the second thing is that near this dynamic freezing, I find a long time value which is below the ETH limit. So I have a subthermal steady state value of the correlator as opposed to a superthermal one, which was also not seen for the Z2 state. So let me just tell you what the dynamics is like. So in the high frequency limit, I just have the steady state. Okay, so this is what the dynamics looks like. Okay, as a function of the number of cycles. Then as I decrease this to between omega d, between let's say 10 and 8 in this regime, what I find is that I have coherent oscillations. Okay, and you have superthermal value of the average. Okay. Then at around omega d equal to 8, a little less than 8, I find that the O22 just remains at its initial value. There is no evolution at all, and that value is 0 because you have started from a vacuum state with 0 Rydberg excitation. And finally, when the system reaches for omega d slightly lesser than this 8, what I find is that the system reaches a thermal value, no oscillations. It reaches a value which is subthermal, which is below the ETH predicted results. Okay. So I'm just going to, let me just try to explain. So the first thing that we note is that here, where there is this in the superthermal regime, this oscillation happens for scars, but these scars are completely different compared to what we found for the Z2 ones. And in fact, what we found is that there are two types of scars which coexist with each other. The green ones are the ones which has overlap with the Z2 state, and the red ones are the ones which control the dynamics here, which has overlap with the 0 state. Now these scars essentially do not exist at high frequency limit, so you don't see them in the Hamiltonian, in the Fluke Hamiltonian in the high frequency limit, but at that frequency range, there are this extra set of scars. So that's one of the things that we found out, that your system can have multiple type of scars when you drive them. Okay. The second thing is about dynamic freezing. What happens is that this kind of freezing happens when your evolution operator doesn't evolve the state. Now, because you start from a Rydberg vacuum, any term in your Fluke Hamiltonian which has this sigma minus is going to annihilate the state. Okay, so it turns out that if you look into this problem, that all higher order terms in the Fluke Hamiltonian has this sigma minus state. So to understand this scarring, you just need to consider the PXP type of term. Because if you consider, for example, the non-PXP type of term, which we derived out here, you see that they are always going to have a sigma minus one way or the other. Okay, and that's going to annihilate your state. So those are not going to contribute to the evolution anyway. So we just consider the PXP type of terms out here. Okay, so and this shows that there are dips in the oscillation frequency at special values, which can be understood from the fact that the norm of the Hamiltonian, which is given by the mod square of this and that, essentially becomes very small at these frequencies. And this essentially means that your Hamiltonian is not going to evolve. Okay, but this doesn't give you exact dynamical freezing, which we observe from exact numerics. To understand that, we do a really small calculation where we just take 3 sides of the chain. Okay, and because 2 Rydberg atoms cannot exist side by side, we have just 2 states in this 3 side space. One of them is when all Rydberg atoms are down, and the other one in which only 1 Rydberg atom is in the up state. Okay, so which means that here there is 0 Rydberg excitation, and here there is 1 Rydberg excitation. So if I look into the space of this Hamiltonian, I can find out everything analytically. And then I found that there is a drive frequency at which the matrix element between the ground and the first excited state just vanish. And that is given by this lambda square plus W 12 W square cos something equal to delta naught. And essentially this happens, one can see this when delta naught is half the drive frequency. Delta naught, so omega d is delta naught by 2m, where m is an integer. Okay, so this essentially means that when this is there, there is no matrix element between 0 and 1, which means that in this space, if you start from 0, you are going to stay at 0. Okay, and this is the dynamic freezing. And this also tells you that if you have a dynamic freezing frequency of, let's say, 8, which corresponds to m equal to 1, you are going to have 1 at 4. Okay, and this is verified in exact numerics. You see that there is one dip at around 8 and the other dip very close to 4. So, and the other thing is that this drive frequency really matches very well with Fluke. The red one is the exact one and the black one is the one obtained by this really small calculation, and they match each other quite well. Okay, so so now what we want to do is that this delta naught, of course, is the static energy gap, which is given by square root of 12 W square plus lambda square, and therefore when delta naught T by 2 is of the order 1, you see that this thing goes to 0. Okay, so that's mainly the physics of it. So it turns out that there are special frequencies at which the matrix element of moving from the Rydberg vacuum state to the next excited state goes away, and that these are the frequencies at which the system freezes. Okay, so this is an example of many body dynamic freezing, and this is one of the ideas or paradigms that my colleague Arnav Das first pointed out in his seminal work. But this is one of the first examples in a non-integrable many-body system which one could find. And finally, I'm going to talk about the subthermal steady state. So this is just a numerical observation that one finds that there is a range of frequencies at which the system does reach a steady state, but it's subthermal. That is, its value is smaller compared to that predicted by the ETH. We have some conjecture why this happens, but we are not really very sure. Numeric certainly shows that this is the case, but I'm not going to get into the details of this. We can discuss this, if you have questions, but let me just conclude. So what I wanted to say in this colloquium is that the quantum scars play a central role in dynamics of correlators of Rydberg chains. And for dynamics starting from Z to state, the drive frequency may act as a tuning knob for reentrant transition between non-ergodic and ergodic regimes. And this tells you, and this shows you that you can use this drive frequency as a knob to tune ergodicity property of a many-body system. Here you use quantum scars for this, but maybe in other contexts this paradigm is going to work. And for dynamics starting from the zero state, you see things like dynamic freezing and subthermal steady state. And these are effects which one would like to see in realistic experiments performed on finite Rydberg chains. And I hope that these are going to be performed someday, which would be a test for our theory. So with this, I think I'm going to stop, and thank you for your attention.
Thank you, Krishnendu, for a beautiful talk. It was quite wonderful. And now we have a time for questions. So this quantum scars, will it depend upon the initial condition? So it might happen that for certain initial condition, you may miss some scars.
No, the scars are actually, it's not really like that. The scars are always present, okay, in the eigenstate of your Hamiltonian. But the point is whether they show up in the dynamics depends on how they overlap with the initial state. If they have large overlap with the initial state, then of course you are going to see their effect in dynamics, otherwise not.
Okay.
Okay.
And you mentioned about the noisy drive. So have you basically studied for?
Yeah, actually we studied this. I am sorry, I don't think, well, I'm not sure if I have anything out here. Let me just try to, yeah. So we did study some random drive protocol. So I can tell you what this is. So we drive it by two time periods. One is t plus delta t or t minus delta t. And this plus or minus is chosen at random, with alpha being a random number, which is either 1 or -1. It's like telegraph noise, okay? So again, you do the same thing. You just study this chain of this u plus, u minus, and they occur in random. Okay, and you can see.
This will have problem with the Floquet, right?
No, for each drive, it's periodic for each cycle. But you are just taking the cycle. So for one cycle, it has t plus. The next cycle, it's t minus. Then again, t plus. For each cycle, you can do Floquet individually, but then you have to take the product of these u's individually. One by one to find out what happens after n cycles of the drive. Okay. And here we find that there are two things. Okay, so I don't want to get into the details of this, but the point is that what we find is that there are special regions, okay, which is given by these blue dots out here, okay, where you have this ergodicity property, and for the rest you don't. Okay, so and this depends on how strong your noise term is. Okay, this dt by t.
Yeah.
So I'd really like you to sort of refer to, I mean, sort of go through the, the original paper for the details of this, because this is going to take a lot of time if I have to explain this in details. Sorry about that, but the main message is that you can use the strength of this noise to tune the ergodicity properties.
Okay.
I have one very sort of naive and possibly a little stupid too. Do you, because you are carrying on with the same definition of thermalization, which had even without a drive. So could this be true that you have to redefine your thermalization and with drive, so that the scars actually, the red dots that you have which merged with the the black band, actually your thermalization or the the red dots where they are separated out from the black region, they also define
no, but
thermalized
see,
states.
no, but you see, there is a problem with that. The point is that the thermalization is defined with respect to eigenstates, either of either the Hamiltonian or the Fluke Hamiltonian. It really doesn't matter which one. So you are given an Hamiltonian that might be your standard starting Hamiltonian or some Fluke Hamiltonian or some any goddamn Hamiltonian that you have. Okay, and then each state of that Hamiltonian, you just analyze whatever entanglement entropy you have and whatever average energy you have. Okay, if you have finite average energy with area law entanglement entropy, you call those states as scars. Now the question is, dynamics comes in because this, if there is a set of states in these eigenstates which are scars, and if they participate in dynamics, then you see their effect in dynamics. So it's only the effect of the scars and which appears in dynamics. Their existence doesn't really depend on the dynamics part. Okay,
That's true. And also plus you add it with the fluctuations that you saw and so on.
Yes,
in the dynamics. Yes. Yeah.
Okay, any further question?
The students are there. Please ask Professor Sengupta. Is there a similar thing on the SSH model with interactions? Because we have a number of SSH experts in the department.
Yeah, I'm not too sure. I haven't really studied this SSH thing, but the thing is that the thing to check there for finite size SSH chain, for example.
Okay.
The finite size SSH chain would be to basically look at the different states in the eigenspectrum, okay, and see their half chain entanglement entropy. The first thing to check is that whether scars are at all there. But normally I wouldn't expect that, because one of the things that really help in formation of a scar is having constraint in your Hamiltonian. So the Hilbert space has to be a constraint Hilbert space. Here, of course, this not having dipoles in two neighboring sites play as the constraint. But in SSH Hamiltonian, I don't think there are these constraint kind of things. So I wouldn't expect this, but I don't know, because precise condition for realization of scars are not known to the best of my knowledge.
So what about Majumdar-Ghosh type of interactions and so on?
No, not those, but I don't really know. But the point is, one of the type of spin models that I know where this kind of things are there, which this my colleague Arnav Sen is now studying, is that there is a class of spin models where you have this Gauss law for their low energy part, this in-out rule, so to speak. So these are spins on a tetrahedron, and two of them has to be in and two of them has to be out, so that the total spin on the tetrahedron has to be 0. That's called the in-out rule or the Gauss law, because you can write it as divergence of some field equal to 0. And so if you look at those kind of constrained Hilbert space again, where the constant is provided by this Gauss law, then you can have scars in their Hilbert space. That's what Arnav's recent work has found out. It's not yet published, but this is going to come out very soon.
There's a student asking. Go ahead.
Yeah.
Ashirwad, go ahead.
Hello, sir. Hello.
Hello.
Yes, sir. So how are you differentiating this scars and this erodic phase based on this entanglement entropy versus energy figure only?
Yeah, so what happens is the following. So let me go to that figure. Let me just give you the first figure that where is this? Yeah, this figure. So you see here I have plotted the half chain entanglement entropy as a function of energy. Okay. So if I just look at the center, which is around this 0, okay, you see that there is a lot of state out here which is very large entanglement entropy. Okay.
Okay, sir.
Do you see that?
Yes, sir. So what is this color showing here?
The colors are not important. I mean, just think of them as black dots, and that's it. Okay. So this region is roughly what ETH is going to predict for you for the infinite size system. But this is a very finite size chain, so this color really doesn't mean much. But the point is that, look, I mean, there are a lot of states which are in the middle, which and these states in the middle have typically finite energy density. All of the states in the middle have finite energy density, but some of them which are in the band have very high entanglement entropy. Okay, which means that these are the states, and you can check this, whose entanglement scales as L. So if you increase the system size, it's going to go linearly with system size. However, these things are below, and again you can check this by carrying out numerical simulation at different system size. Their entanglement scales with log L, and therefore they are small. You know, for reasonable L, L is much larger than log L usually, right? So those are the small L things, and those are the ones which has finite energy density, but area law entanglement. Okay, so that's how I distinguish.
Yes. Sir, one more. This is a little bit out of context, but yeah. So if we put, I have seen one figure where if we put disorder, then the entanglement entropy decreases and becomes like saturated.
That's right.
Then that is many body localized in the many body localized.
That's
phase.
right. So that is the many body localization.
Okay, sir. Can we plot this exact figure for many body localized phase? And
yes, you can. Sure. Sure.
In that case,
there you would see that every state in the spectrum, and not just a few, is going to become an area law kind of thing. Okay, because if you add disorder in the many body localized space, you know, all the states in the Hilbert space in one-dimensional problem, they become localized. Okay, and they have area law entanglement. Here, there are two differences. One is you don't have disorder, and the second one is that you don't have you have only a few states which have area law. Those are the scars. But if you do this for the many body localized phase, all the states are going to show area law. So if you come from weak disorder to strong disorder limit, you are going to see that initially you are going to have a thermal band where you have volume law entanglement, but then everything is going to become area law. Okay. That way you can distinguish where you have entered this many body localized phase.
Okay. Okay. Thank you, sir.
Okay.
Okay. Any other question? So if not, then let's thank Krishnendu again for giving such a beautiful talk, colloquium talk, and we are really thankful for him for giving the colloquium at this level, and due to some technical difficulty, we could not complete it last time, but he kindly agreed to deliver it again today, and it was a very beautiful evening for all of us. And with this, I would like to thank all of you for actively participating, and this is also the last colloquium for this semester. So we hope we'll continue again in the next semester and see you all in the next semester. So we also would like to thank our technical staff, Basav and team members for technically organizing this talk. And with this, we conclude the session. Saurabh, you want to add something?
Yeah. Of course.
Okay, may I just say one thing? Thank you everybody for patiently listening to this, and I enjoyed it quite a bit. Thanks.
In fact, a lot of thanks due to you because of this. Once it got cancelled, and then you quickly agreed. So we all are very thankful to you for quickly agreeing once more.
Of course. I of course is not that busy a person, so no problem. So
No,
yeah.
it was real good talk. I mean, I wish that many more students probably. I don't know why they could not attend, but there's a large number of people working in condensed matter theory, and would be interested to like Pankaj, myself, Tapan, Girish, all are there. So thank you very much.
Yeah, thanks a lot.
And
Sumitra.
Krishnendu, once
Have you in
things
person.
become normal, we would please come here, and it will really be very fantastic time for all the students to directly interact with you. And
I would love to. I mean, when
because now
things
we have
become
a big
normal,
group in condensed matter theory, so
yes,
student will be very much motivated to talk to
sure.
you.
No, I would love to actually. Anytime after things become normal. Okay.
Okay,
Okay.
so
So yeah. Okay. Bye and be
bye.
safe. And yeah.
Thank you all.
Thanks once again.
Sure.
Thanks
Bye.
once again. Yeah. Bye. Bye.